computer? Okay, nice. Okay. Thank you for reminding me of that. All right, so now I'll read it. Let's see, we've got 4 protons are held together at the corners of a square. Am I reading the right one?
Mm-hmm.
1 centimeter by 1 centimeter. Okay, if one of the protons is released, so only one, and flies off from the other 3 protons, what is the speed of the proton when it is very, far from the other 3? All right, I'm going to draw a picture here, and then this will give me a chance to see if I can share my camera, my iPhone here again on this different computer. A little slow. Come on. Try that again. Okay, there it is. All right, so let me go to my camera here. I hope this old laptop's not too slow. Fortunately, I only have to use it for the first hour and a half here. Oh, okay, good. Looks like it popped up. Nice. Zoom in on the piece of paper a little bit. You put something there, you can see it. Good. All right, little choppy, but not bad. Okay. All right, Daniel. So, as you said, this is number 1. It's from the practice test. And I'm debating if I should look at the solutions. You said there were 2 calculations.
Well, it's like a formula, but it has like 2 KE. It has like 2 different pieces added together. I just don't understand how you got that.
Okay. All right. But let me begin with a concept first. That is, I hope when you read this, you see in that question the conservation of energy principle. The fact that they're saying, okay, how fast does it go? All right. Then, so I'll just write here energy. So if you see the conservation of energy, then hopefully also in your mind, you see the idea of calculating the potential. Because we know this, that the change in potential energy is equal to the charge times the change in the potential. Okay. And so if I didn't get this across in the video lectures, let me emphasize it now, is that the hard part of this problem is really calculating the change in the potential. Then the rest kind of falls into place. Not to say it's easy, but a lot easier. All right. So I'm going to do this. I'm going to say, okay, what is the initial potential? Oops, initial.
Okay.
And then what is the final? Because when I subtract those 2, then I can say what's the change in the potential. Now, coming back to our lesson, if you will, the potential from a point charge is given here by this formula. It's Coulomb's constant times the charge divided by the distance separating the 2. All right. So let me go back to the problem. I don't think the problem said which one moved, other than it was just one of them and they're all the same. So if I'll maybe circle this one in red and say, all right, this is the one that's going to go shooting out and it's going to leave. And so what is the change in potential? And that's where this first equation, what's the initial, is going to come into play, because I would say, there's a potential 1 and a potential 2 and a potential 3, because there's a potential created from the other 3 charges. In fact, if I just label them, I'll just start in the upper left-hand corner and call that one number 1, going down here to number 2, and going down here to number 3. And with that in mind, here's why I guess I wanted to emphasize that. If you look at the solutions, they only have 2 calculations, but there's really 3, because 1 and 3 are really the same calculation. They're the same charge, they're the same distance away. Okay. So you could write that as twice the potential from number 1 and then plus number 2. And so that, I think, let me scroll down to the solution, I think is what the author is doing first.
Oh, yeah. I see. Okay, so that's why he only had two things instead of 3, because he just did 2 times one of them.
Yeah, and so he writes it like this. He writes it as 2 times, and then he puts Coulomb's constants, and then he puts E for the charge of a proton, and then he says the distance is 1 centimeter. And so that's kind of the first step.
Okay.
And then the second step is to worry about the potential from number 2. Now, number 2 is being along the diagonal, and so it's further away. And so he writes Coulomb's constant. I believe Don did the solution. Looks like his writing. And then the charge, which is E. And then he puts the 0.01 and he multiplies it by the square root of 2. And you may or may not remember that from your math class, but if you take a triangle that, in this case, is an isosceles right triangle, where this is A.
That's the hypotenuse, right?
Right, and so that would be the length of the hypotenuse when you have a isosceles right triangle, because you would have A squared plus A squared is equal to C squared. And so you would have 2A squared is equal to C squared. And so when you take the square root, you get root 2 times A. And I don't think he worked that out in the solution. He was kind of just...
Yeah, I
hopefully
figured that out eventually.
Okay.
All right. Cool.
Does that answer your question? I keep going.
Yeah, that I just like you said, I thought there were supposed to be 3, and I just couldn't figure out why he had the 2. I couldn't figure out where the 2 came from and why there were only 2, but that makes more sense now.
Okay.
Cool. Thank you.
Nice. You bet. All right, let me switch my screen back over to the Zoom, see if anything. Let me turn on my chat here. What did I mess up? There we go. All right. Well, no one threw anything into the chats. I don't know if the other 2 of you want to join in, or if you're just hanging out to see the solution. Got a question?
Can you explain number 2, please?
Yeah. Now, number 2 on this practice test also?
Yeah.
Okay. All right. Good. Let me get this one out of the way here. Actually, I'll even write down on my little sheet here, number 2 on the practice test, so I can kind of organize the, I should have started a timer. Well, next time I'm going to figure this out and get a timer. I use my phone for the display here, so I don't have the timer. All right, but I'll just start here. I guess I'm still sharing my screen, so this will be good. Number 2, and let's see, little choppy. Okay, that's. You know what? Hang on, I'm going to get to some line paper. I think the autofocus might work a little better. have any more line paper. Oh, bummer. I used it all up here. Oh, I got. Well, maybe it'd be good to use this up. This is supposed to be nicer paper. I don't like it. It's a mistake to buy this paper here. Let's see if the autofocus comes in a little better. Okay. Yeah, I think I like that better with the, get something the camera to focus on here. All right, so number 2. And like I said, a little glitchy, but see, yeah, look at this fancy paper. It's got this plastic along the edge so it doesn't tear. It's a little thicker, but it's not very fun to write on. All right. So number 2. So I need to come back here and read number 2. Number 2 says what? It says a uniformly charged insulating rod of length 14 centimeters. All right, so I'll start off by just kind of drawing a rod. And it's 14 centimeters. Oh, and then it's bent into a quarter circle. Ah, okay. So maybe I'll try to draw a quarter of a circle. Bend to the shape of a quarter circle as shown. Oh, I skipped right over the picture. Okay, yeah, okay, so I see the picture. The rod has a charge of, and so Q on this rod is negative 7.5 microcoulombs. Find the magnitude and the direction of the electric field at the center of the quarter circle. And then we got a couple of hints here. All right, so the picture and my grid, this will be the radius of curvature here. And maybe I'll just start conceptually, and which will give me the direction, because if this rod is negatively charged, I'll put a bunch of negatives by it. Then what I'll have, let me switch this one back over to my Zoom screen. Okay. So then what I will have is, like if I looked at a little piece of charge on this quarter circle, the electric field would point towards that quarter of a circle. And of course, another little chunk of charge would also point towards that. And so I'm going to just start here conceptually and saying I would have a bunch of little electric fields pointing towards this quarter of a circle. And so when they all added up, there would be a symmetry about them along this 45-degree line. And it almost would be easier to imagine if I made maybe a grid that looked like this, where I had a quarter of the circle kind of taking like an umbrella look to it. And so I have this 90 degrees making my quarter of a circle. And so conceptually, I would say that the electric field then would ultimately be, and in my second grid would be up. And so I guess to answer the question as the picture has it, the direction of the electric field would be at a 45 degrees into quadrant number 2, I guess is the way I might describe that one, and say, all right, so at this 45 degrees for quadrant number 2, that's the direction of the electric field. So that's the first part of this question. What direction is it? Now, of course, this is where the math kicks in here, and I would have to do something. Now I'm wondering if I should use this grid I just made. I was trying to do that just to get you conceptually to see, or should I go back to the first grid? Yeah, I think I'll go back to the first grid because I think that would have been probably what a student would have done. They would have said, well, this is the grid they gave me. This is the picture they gave me. All right. So coming back to this grid, and maybe I should have never even drawn this one. Maybe I should have just argued here that there would be then X and a Y component, but they would be identical. Maybe that's what I should have done. They would be split. The total field would be right down the middle. And the reason that is important here is because I'm going to write down what is the electric field in the X direction. And I'll only do magnitude because if I come back to the, to the picture, my camera zoomed in a little too much. I'm going to take it out a little bit. All right. So if I come back to this one here, the picture that is, there's a little delay in my old laptop, so again, I need to get my new one back here after 12. But if I go ahead and just look at the X components and add up all the X components from all these chunks of charge, then whatever I get for the X component, I'm just going to say it is equal in magnitude to the Y components. And so that's going to be my logic here. Put a little more light on it if things would look better. Tapped on the auto zoom. Now mine, it doesn't look real focused. Is it focused enough for you guys?
Yeah.
Okay. All right. So with that in mind, I'll just do the X component and write it this way. And I have a feeling maybe this is more along what you were really after in this question. You're saying, okay, and then how do I, add them all up? And so this is straight from chapter 20, what chapter is it? 23, where we do the Coulomb's law. And so we learned here that the magnitude of the electric field is Coulomb's constant times the charge you place there divided by R squared. And so that would be the magnitude of it. And then to get to the X component, I would have to multiply by either a sine or a cosine of some angle. That angle would depend upon which angle you pick. So I'm going to come back to the picture here and say, well, why don't I focus my attention on this angle? I'll put it in red and say, okay, if I focus on that angle, then I would want the adjacent to that, and that's where the cosine function would come into play. In fact, just out of my own curiosity, I'm going to go to the author's solution in here. And what angle did he look at? Let's just see if we're doing something different. And good. And he draws it in his picture. Oh, he measures the angle from the 45 degree. Okay. So we are a little different, but maybe that's good here. All right. So I'll come back to this and say, all right, let me keep going, because then I've got this integral. Here's where the hint comes in, is that if we think about lambda being the charge density, then a little bit of charge divided by a little bit of length, and I'll write the length as a ds. I don't want to use an x or a y here, because the x and y is really a grid that I have on here, and the arc is really what I'm talking about, the charge of the arc. And so let me write this as lambda ds, and then r squared cosine theta. I'm going to put page 1 here. Okay. And so that's kind of that big piece. Let me just kind of shift that paper down here and keep going. Because then I can write, and I'll just repeat everything except for the ds, and I'll use this as a chance to just remind yourself that the arc times the radius times the angle, or maybe I should say, sorry, the arc length is equal to the radius times the angle, which means that a little bit of arc length would be the radius times a little bit of angle. And so I can replace my ds with r d theta. And once I do that, one of the r's upstairs and downstairs cancels off. And then looking a little closer at this integral, wondering if the red would stand out better. The integral, let me do this. Let me just make another line. But I would say that the constants should be pulled out. And they said it was a uniform charge density, so the lambda is the same and Coulomb's constant is the same. And so then we have this d theta, and then we have the cosine. And the way I set it up, coming back to the picture here, I just am going to just start with theta equaling 0, and so that would be kind of this little vector, and I'll just keep going until I get to a theta of 90 degrees. Maybe I'll call it pi over 2 for radians, and so my limits would be 0 to pi over 2. And I have a feeling, since the author who did the solution kind of did it at the 45 degree, they probably just went to pi over 4 and then doubled it. But I'll look at that in a moment here. So this is Coulomb's constant times lambda. And now the integral of a cosine is a sine. And then, of course, evaluated from 0 to pi over 2. And maybe then I think about the integral. That's not the negative one, is it? It's the one, yeah, no, that's a sign, not a negative sign. And, oh, and I apologize for earlier on back here. I when I went to pull out the constants, I forgot the r all the way along here. So let me fix that before I go too far. Yeah, back here in this integral, I pulled out the numerator. But one thing that was also a constant, and this is where the quarter of a circle makes it an easy problem, or easier, is that the radius doesn't change, and so I can pull that out. That's nice because this is really then sine of pi over 2 minus the sine of 0, which is 1 minus 0, which is just equal to a 1. And so that makes dealing with the trig function pretty easy. Excuse me. And so I get Coulomb's constant times lambda over r, and that is, as mentioned earlier, the magnitude of the x components. And as I said earlier, and we'll repeat again here, that is equal then to the magnitude of the y components. And so maybe if I redraw my grid here, and so I'll put the quarter of a circle here. But I now have come to the conclusion that I have an electric field in the x direction and an equal magnitude electric field in the y direction. And I must say this might have been the advantage that the author who did this didn't have to mess with the two different components. But I think it's a little easier to see this way. So that's kind of why I went with it. But the total result then would be Pythagorean's theorem. And so you would say E now total. And since the x component and the y component are the same, we're back to this isosceles right triangle that I was mentioning in problem number 1. The magnitude would be the square root of 2 times the length of one leg, and we said the length of the leg would be Coulomb's constant lambda over r. Now we've got some numbers we have to put in, and so there's still some more work, but I think we've done the meat of it. But let me put that off to the side for just a second, because I can't calculate anything until I get the r and the lambda. And so I'll come back to that. Let me just call that page 2 here. Go on to a page 3. But why don't I start with the lambda? The lambda would be the same as the total charge over the total length. And they made it very clear that there was a charge of, and I'm going to just do magnitude, because back here, this equation, I'm really doing magnitude. So let me not worry about the negative. As we said earlier, we know the direction of the field. It would be at a 45 degrees in that second quadrant. And so I'm going to put a 7.5 microcoulombs for the magnitude of the charge. I'm not going to put the negative of the charge, just its magnitude. And its length was 14 centimeters before we bent it. So even when we bend it, it's still 14 centimeters long. So it's 14 centimeters along a bend. So the charge density should be 7.5 times 10 to the negative 6 divided by 0.14. And so that should be the charge density. And so this is 5.36 times 10 to the negative 5 coulombs per meter. So there's my charge density. And maybe just as hard is to figure out the radius of this. But we know that the whole length, which was 0.14 meters, has now become a quarter of a circle. So the circumference of a circle is 2 pi r. And so if I put a 1/4 in front of 2 pi r, I should be able then to figure out the radius. So here's the radius, and grabbing my calculator, I got the 0.14. I guess at first I'd multiply by 4, then I would divide by a 2, then I would divide by a pi, and so when I hit enter, I get a radius of 0.0891 meters. Yay. And so there's my R. Okay, let me come back to page 2 then. All right, so maybe I'll just recopy the answer from page 2 here. So on page 2, we said that the magnitude of the total electric field is the square root of 2 times Coulomb's constant. So there's the 9 times 10 to the 9th times the charge density, which we just got a moment ago, 5 times 36, or sorry, 5.36 times 10 to the negative 5. So there's the charge density. Then divided by the radius, which 0.0891 is what we just got. So now I can finish all of this by saying, all right, let's take the square root of 2. Ooh. Try that again. Square root of 2, and then come out of the square root. Okay. Then times 9 times 10 to the 9th. Then times 5.36 times 10 to the negative 5. And then divided by 0.0891. I get a number of 7 points, and I'll just do 3 significant figures. So 0.66 times 10 to the 1, 2, 3, 4, 5, 6. There. And I suppose one last step to be careful with these units. Coulomb's constant is squared over Coulomb squared. And then, of course, if we have a Coulomb per meter up here for the charge density and a meter down here, the meter squared will cancel off, the coulombs will cancel off, and we will get the appropriate unit for the electric field, which is the newtons per coulomb. So I got 7, and I'll jump over here to the author's solution, and did the author stop? The author left it in symbol form.
Yeah, that's why I was a little bit confused, because I didn't know how to get the radius. But
Oh, okay. So I maybe I trust you saw that. I'll highlight it in blue here again, but there's how you get the radius.
Thank you.
And might be a little choppy. I see it saying something about. Oh, there we go. On my desktop, because I'm kind of watching. But yeah. And, it sounds like that was your magical step, right? The radius.
Yeah.
I have a quick question on this
Good.
problem.
And that wasn't even part of the electricity stuff. That was just some geometry. Yeah, go ahead, Jake.
Could you have thought of this as a complete ring and then taken
lost.
Maybe I'll type it in the chat.
Hang on here. I'm not hearing you real good, but I think you said, okay, it's about a ring. And yeah, go ahead and type it in the chat, but I'll say this as you're typing, a ring doesn't sound promising, because what will happen is the charges will be uniform all the way around it, and you'll get 0. And what you're really saying is, I've got quarters of a circle that when they add up, they're equal and opposite, and they come out to be 0. And you don't really know then what the magnitude is of those individual pieces are. All you know is that they're like, of them are equal and opposite, but you don't know their number. You just know they come out to be 0. All right, good. I see your question. Could you have thought of this question? Yeah, good. I'm glad you're right. Okay, yeah, no, you can't, because of the plus and minus. I'll even simplify it. If you just did 2 numbers that were equal and opposite, and all you know is they add up to 0, you don't know what they are individually. All right, good. Chase here has a question. Let me check my response time. Yeah, I'm going to stop sharing mine for just a second. I know that sometimes when I stop sharing and then come back, things stabilize a little better. Like I said, it could also be this older computer, so hopefully that will be solved when I get my better computer back here. All right, so Chase, you got the next question here. It says, can you go up the beginning of the problem and go over the components? Oh, absolutely. Yeah. So let me, and I'll turn back my sharing and see what comes on here. But I'm going to come back to the picture here. And now I'll go to share screen. Let me try my camera again and see if it's a little more stable. All right, let's see what's going on. Oh man, I keep saying sharing screen has failed. Oh. Okay. What if
On the test, are we gonna have to calculate the exact number of every single question, or are there gonna be some questions where it's just leave it in component form?
Usually there's both.
Okay.
Yeah,
cool.
Yeah. So I guess because some of them are questions that say, things like, find the function, and so they're after a function. And so maybe you know all the other numbers, but you want to leave it as a function of R, because they're not saying find the electric field at a particular point. The key step in this one, though, was they actually said, at a particular point.
Okay. Cool.
All right. And I'm going to try this again. I came back and said I cannot share my screen for some reason. Yeah, screen sharing has failed. Please try again. Now, let me just try something a little different. Let me see if I say let's let everyone share. I don't know if this will help because I can't write on this desktop screen, but I'm going to go to my desktop and just see if I could share something. Here, I'll do the textbook. That's a good sign. Okay, so I can share from my desktop here like you guys can. Well, let me stop sharing. I'm going to try it one more time, but then I got another idea. And it's, like I said, this old laptop, I can't go to my screen. So I may, no, it says can't share. But let me see if this helps for just a second. I'm going to share my Chrome here from the student one. Okay. And I wonder if bummer. Can you see my mouse here? I guess here's what I'm trying to point out. Maybe I might reboot this meeting so I can share my camera again. But this, if you think of this vector as being the electric field, then there would be a horizontal component, an x component, as well as a vertical component. Yeah, now I wish I had my white screen here. But what I did is I put in cosine of this angle right here. So what I was calculating was just the x component. And then I went from an angle of 0 all the way around this circle of 90 degrees. And that gave me then the total x component of all the pieces. And then recognizing that if I looked at this thing sideways, the x component and the y component would be exactly the same. So all I did was go ahead and work out the x components and then say, well, the y component is going to be the same. So if I got the total, I would just do Pythagorean's theorem and I have the x component and multiply by the square root of 2 to get the total. And so with that said, I'm going to jump in here as host and see if I can share anything. It'll just kick me off there as a student. Okay, that works. And okay. And let's see, I don't have a touch screen on for this one. But if I make a vertical line with my mouse, yay. All right, Chief, I'm going to try this. And a horizontal, yay. Okay. And then if I were to draw a half circle, ooh, Yay! All right. I hope you're having as much fun as I am. All right.
I look like my drawings with a pencil, so.
Okay. All right. So if this is what I was trying to say in words, and so if we took a little chunk of charge right there, okay, so there's my chunk of charge, and you looked at the electric field, remember that's a negative chunk of charge, so the electric field would point towards it. So I'm going to come from the center towards it. I'm going to try to put a little arrowhead on it. Yay. Oh yeah, I'm definitely looking forward to getting my laptop back. All right. So what I might be able to do, what if I could change colors? I know with the Microsoft whiteboard and the touch screen I can, but this one I don't immediately see it. Oh, there's an arrowhead though. I could have done an arrowhead. But what I was trying to say is this vector here can be thought of as a x component. And that's kind of hard to see because it's actually on the x-axis plus a y component. And so if I only want to get just the x component, so what you might say the electric field in the x direction. So this was that first step, and then I'll see if I can share my camera here in a second. But what I would do is to add up all the electric fields in the x direction. And so right here, this angle, if you call that theta, then this would become the magnitude of the electric field multiplied then by cosine of that angle, which I called theta. And then that's where I said you can replace the magnitude with just Coulomb's constants. The little chunk of charge right here, so that little chunk of charge right there, and then its radius squared. Yeah, let me go back. Since I did all this on the camera, I wish I could get the camera right. So I'm going to try it one more time here in a second. But that's kind of the equations of the words I was trying to say. I don't know, did that help at all?
Yeah.
Yeah. And then I'll hit stop sharing and come back to my camera, see what it gives me this time. Yeah, it failed. It doesn't seem like it's my Zoom. Maybe it's my phone.
Zoom takes a lot, so sometimes it's just laggy. Like it takes a lot for your computer to handle it sometimes.
Okay. And actually, it makes me think that maybe I'd be better off Yeah, to share my laptop, because then I have a mouse I can scribble with. And maybe that's a little easier. I'll do that if I can't get the phone here to work. But like I said, I should get my laptop back at about 12:15, so I should be good to go for better equipment. Although this doesn't seem like maybe it's my laptop. It seems like the phone lost connection. Anyways, I'm chit-chatting away here, but who was it? Chase, did I answer that enough, or should I draw some more?
Yeah, I think I got it pretty good. Thank you.
All right. Yeah, sorry that didn't work out so well. And I'm going to ask you guys for the next question, but I'm also going to take my phone, and it's been a long time since I've powered down my phone, so it might be worth powering it down. And there we go, and doing a reboot. Okay. There we go. All right, so my phone's really. All right, so I'll come back here, and while the phone reboots, maybe my connection will be a little bit better. Anybody else got a question? I'm looking here at the chat on my laptop, nothing. And I guess the chat would be the same here as the desktop. I'm going to play here. Let's see, so can I share my textbook? Good, that seems to go okay.
You said in your email the test was going to be 5 questions, right?
Yes. Let me take that as an opportunity to say my tests and haven't changed just because we're online now, but they're just one question, just like a homework on the top of each page. Well, in this case, I guess I won't give you a bunch of pages. If it was a handout one, I'd give you 5 pages and it'd be on the top of each page. But I'll just give you the 5 questions, and you'll just see them, and you probably want to do each problem on one page, but and so you can scan them individually and turn them in. But yeah, 5, and so that's on 25 minutes a problem is what it's come out to be. And then for lack of not knowing what else to do, I said, well, let me give you some upload time, and I'll just go 25 minutes for upload time, and that's how.
Okay. So each problem should approximately take about 25 minutes to figure out at the most.
Yeah. I mean, of course, that's average, because I think some of them are less and some of them are more.
Mm-hmm.
Mm-hmm. And it's also difficult to answer that too, because 25 minutes. I guess I would say the 25 minutes, if you've been working with the material as you have been, it'll take you 25 minutes per problem. But sometimes people come into the test without doing but one or none of the homework and think they can do it in 25 minutes. And the first time through, you can't do these problems in 25 minutes, as you know during the homework.
Yeah.
Is it gonna be just like on a Google Doc that we download or something, or?
Oh no, it'll be. Well, now that I rebooted it, I got to. take my camera off the stand. It'll be on Canvas. So it'll be right in the canvas when you click on it. It'll just be right there on Canvas. How am I trying to say? The labs, for example, you've done 4 labs. So if you just click on one of those labs, you'll see that there's a little description in the lab. It says, watch these videos, and then I've got the 3 links, and that's exactly what you'll see on Canvas. You'll say, do this problem. And so I would suggest that you just take a pencil and paper and leave the question on the screen and just say, okay, here's number 1, and just start working out number 1. And, that'll take a whole page, maybe 2, depending on how efficient you are, and then go to the next one and do the same thing. And so then when it's all done, just go ahead and scan page. Well, you can do it however you want. You can scan them all in one big page, or so you have 5 pages that you turn in as one PDF, or you could do it as 5 separate ones. That works too. And I've been telling people, if you can't make a PDF, Canvas is designed for PDF, so it works so much better. But if that's a pain, just take a picture of it and send in the picture.
Okay, thank you.
Does the exam start at 8 or 10 o'clock in the morning?
Oh, what I did, for better or worse, is I kind of, in a face-to-face setting, there would be 2 sections of this class. One class would start the test at 8, and another one would start it at 10:30. So I just kind of merged those together and said 9. So let me encourage you to go to Canvas now. And when you go to Canvas, you should see exam number 1. In fact, I'm going to write that down here to myself to just send a message to everyone, because I think everybody should just go to Canvas and see exam number 1 on Canvas and click on it. Now, right now, if you clicked on it, it would just say the window or something like that, the time, or it's locked. I think that's what it says. I think it says it's locked. And so it would just say, hey, it's locked right now, and the window's not open. But it'll tell you the window time. And so you look at it, and it should say this unlocks at 9 o'clock on the 29th. Is that true, Daniel? Looks like you're looking at it. Yeah. And so, and then it will say you have until, let me look, what do you guys have until? 22. So you should have till 11:30. So 9 to 11:30. And so that's 2.5 hours. That's the 25 minutes times 5 plus another 25 minutes to upload. So 25 times 6 is your 2.5 hours. And then there's a few special cases. There's an engineering class that starts at 11:10. So I think you saw that in the email. Any of you guys in the engineering said, hey, just send me a message and I'll bump it up 20 minutes. So they're starting at 20 minutes early and finishing 20 minutes early. And then there's some DSPS stuff too. And I think I've got all those straightened out. So let me encourage you to go to Canvas and click on that.
And my DSPS stuff looks good if it ends at 11:30.
Oh, yeah. So I can't remember if you were DSPS, but if you're DSPS, there should be the appropriate calculation in it. Okay.
Yeah, the time's changed on mine a little bit.
Okay. Yeah. So engineering people and DSPS people have a little different calculation in the formula, but for the most part, they're the 9 o'clock to 11:30.
Could you explain number 5, please?
Oh yeah, sure. On the practice desk.
Yeah.
Okay, so I'm gonna now that I rebooted my phone, I'm gonna try this again. No, dang gummit. It's gonna be frustrating. I might exit. If I exit, will it kick you guys out?
Yes.
It depends on if it's an ongoing meeting, I think.
Oh, we can rejoin.
Yeah, let's give it a try. I think it's worth it. I really like my camera to be working here, and I'm not sure why it's not. So be prepared here to exit and jump back